So the talk today will be given by Annalisa Calamida. She received her PhD here in Tor Vergata in collaboration with DINAF and went on to work as a science officer for the ELT at ESO and at the Space Telescope Science Institute. Since 2017, she is working with the Wide Field Camera 3 at the Hubble Space Telescope, leading the effort of improving the photometric calibrations in the optical and in the infrared. She's particularly interested in studying globular clusters and the phenomenon of multiple stellar populations that happens in them. So today she will be telling us a bit about old stellar populations as a tool to understand our galaxy's formation and evolution. Dr. Calamida, thank you for your presence, and please feel free to begin.
Hello, good evening, everybody. Thanks for inviting me to give this talk. Let me share my presentation. Okay, can you all see the screen and my mouse pointer?
Yes, I can see it.
Okay, again, thank you for this invite. Today, I will show you some results based on ground-based data and space data, mostly collected with Hubble, on all stellar population in globular cluster and in the galactic bulge that we can use as a tool to understand the evolution deformation of the galaxy. This work was done in collaboration to many different astronomers, scientists all over the world. So this is my chain of connection. I'm in the center. These are my collaborators, the largest the name, the most I collaborated with a person. And the first topic of my talk, so mostly the two talks of my talk will be focused on globular cluster. And the last one third of my talk will be more focused on galactic bulge. This is a schematic view of our galaxy. Our galaxy is a spiral galaxy, so here we have a disk. As you can see, towards the center we have what we call the galactic bulge. And then we have a galactic halo that is shaded here that includes many globular clusters, about 160 or more. There are also globular clusters in the galactic bulge, and lately actually many have been found also in this region of the galaxy. And this is the position of our sun, about 8 kiloparsec from the center of the galaxy. So what is important to note here that whenever we observe the galactic bulge, for example, we are also observing through the disk. So we have, like many other stars, gas and dust in front of us. When we observe, like in the galactic halo, like a globular cluster, we still have stars in front of us, but likely a little bit less, so it's a little bit easier. But take into account that every time you observe an object, you're not only observing the stars of the object, but also other stars belonging to different stellar population. So why is it important to study globular cluster? The globular cluster are observed in most galaxies, spirals, elliptical, dwarf galaxy, and they include amongst the oldest stars that are present in the universe. So this means, for example, if we can provide the age and estimate the age of a globular cluster, we can then provide a lower limit to the age of the universe that can be compared, for example, with cosmological estimate of the age of the universe. These are two images of globular clusters. What are they? They're very conglomerate of stars. In the centers, they're very concentrated, so they have a very dense core, and then the density declines following different laws. I will show you this later. And then it tends to zero at some point. This is the center of Omega Centauri. In particular, it's a less dense cluster, as you can see, but it's the most extended and massive that we have in our galaxy. About 20 years ago, a little bit more, so when I was starting my master degree thesis at the University of Tor Vergata, we were thinking that globular clusters were like, globular clusters were simple stellar population, so all the stars were at the same distance, with more or less the same extinction, at the same age and metallicity, but then photometry and spectroscopic studies showed us that actually clusters, they host multiple generation stars, so they're not really simple stellar population. And these multiple generation stars have different light element abundances. So not heavy element like metallicity, but light element abundances. This was a really great discovery and opened up a lot of different other studies to better understand this phenomenon. We still cannot fully explain the presence of multiple generation of stars in globular cluster, and also why the abundance of the light elements of these stars in the multiple generation is different and varies among cluster and cluster. They are different. And we also want to understand how the entire globular cluster system in the Milky Way formed, and also how these clusters in time interact dynamically with a galaxy. For example, some clusters are lost a lot of their mass during the last gigayears, during the first gigayears, and they present some tidal tails, so we want to characterize them. These are just some of the questions about globular cluster studies. There are even more, so they're still very interesting objects. The tools that we use to study globular cluster are the color magnitude diagram, that is the equivalent of the Hertzsprung-Russell diagram, but instead of luminosity we have magnitude here, instead of temperature we have the color. And this can allow us to estimate the age, metallicity, and distance of the star, in particular when we compare it with models. So we compare the color magnitude diagrams with evolutionary tracks. And when a track is estimated for a fixed age, like in this case 12 gigayears, then it's called isochron. And according to in this case, there's a very good agreement. We can then determine the properties of the stellar population in a cluster, in this case is Omega Centauri. Or we can also improve and verify the accuracy of the models themselves. Another tool is stellar spectroscopy. This is a very known tool, and it gives us information on the chemical composition and the kinematics of the star. In particular, this is two spectra collected with HST for two very faint stars here in Omega Centauri. Another tool is variable stars. In particular, R-Lyrae stars are present in many globular clusters. They are typical of all stellar population, and there are different relations, like the period luminosity relation, to determine that can give us information on the distance of the cluster, the extinction, or also a proxy of the chemical composition of the cluster where they are. So this is not a real color magnitude diagram, but it's a composite color magnitude diagram from different clusters that were observed with HST. This was made for 10-year anniversary of HST. Now HST has more than 30 years, so got a little bit older. But I found this figure very cool to explain you the different diagnostic tool of a color magnitude diagram. The most important is the main sequence turn-off. Stars spend most of their life on the main sequence. That's why it's called main sequence, and is where the star is burning hydrogen in the core. At some point, hydrogen is finishing and the star is moving towards lower temperature and is starting to burn hydrogen in a shell around the core. And so this point is a very good indicator of the age of the star when the star finishes the hydrogen, which depends on the mass of the stars. These are lower massive stars and here higher massive stars. And then we have another feature which in some combination of magnitude and temperature is actually horizontal, and is called horizontal branch, and is the phase where the stars are burning hydrogen in the core. So they spend here a reasonable amount of time, much less than the time that they spent on the main sequence, especially for the low mass stellar populations. But it's a good indicator of the distance. So the fainter this branch, the more distance is the cluster. And then we have the red giant branch, where stars, as I said, are burning hydrogen on a shell. And the color of this branch is giving us information about the metallicity of the stars, because it depends on the different kind of elements that are present in the atmosphere of this red giant branch star. The redder, the more metal rich. Finally, we have also a very nice white dwarf cooling sequence here. So the stars finish helium and hydrogen, and in the case of low mass stars, is formed by a core of carbon oxygen. So there's no burning in the core anymore, but the star is cooling down. And the more it ages, the more it cools down, and so the fainter it is. And this sequence indicates also the age of the stellar population. So as you can see, the color magnitude is an amazing tool to understand stellar population, in particular, in this case, low mass stellar population that we have in globular clusters. And why did I decide to study Omega Centauri? Good question. I started studying Omega Centauri in 2003, so many years ago, when I started my master degree thesis. And I was fascinated by this object because it's the most massive of the Milky Way and most luminous cluster. It's different because it has a retrograde orbit in the galaxies in comparison to most of the other cluster. And also is one of the few that shows dispersion of the stars in the iron abundance. It's more than 1 dex. As you can see from the spectroscopic metallicity distribution, this comes from spectroscopic observation. Sorry, it's quite old as a plot. And you can see different peaks here in the metallicity, and these are very well mirrored by photometry, because here you don't have only one red giant branch star, like in this, schematic color magnitude diagrams, but you have multiple branches that are following exactly these peaks. As I told you before, that giant branch depends on metallicity. So the redder is the branch, the more metal-rich the star in this branch. And then here you have the different turn-off, and then you have the main sequence, which has a very, very, very large color spread, right? So maybe this is also indication of metallicity spread. But shall we see like a separation in between the different main sequence belonging to the different population? I will show you later. Now, there are different hypotheses concerning the origin of Omega Centauri. 2 are the main ones. One is saying that Omega Centauri is the relic of a dwarf galaxy that was accreted on the Milky Way. The other one says that Omega Centauri is the result of the merging of 2 different stellar systems. This could have happened either in the Milky Way, but it's not very common probably, or in a dwarf galaxy or a galaxy that was later accreted by the Milky Way. And in fact, thanks to the measurement of our Gaia satellite recently, this is from 2018, this figure from this paper, we actually found out that our galaxy went through a very big merging event with another quite big galaxy called Gaia Enceladus or Gaia Sausage. And some clusters are kinematically associated to this galaxy, for example, Omega Centauri. So Omega Centauri could have been part of these galaxies, or maybe even the nucleus of this galaxy that was accreted on the Milky Way. Here again, the main sequence. So you see the main sequence here, but then you get Hubble. Hubble has a much higher spatial distribution, spatial resolution, and it's a space telescope, so you can go much deeper and study much better the main sequence of clusters like Omega Centauri. And this was done many years ago, as you can see here, 17 years ago. And voila, we found out that actually the main sequence is not a spread of star, but splits in 2 main sequences. One we call it blue because it's bluer, and one red because it's redder. And so what it means, the redder the star, as I said, the more metal-rich they are. So we thought from this photometry that these stars were redder than the bluer ones. But from some spectroscopic data collected with VLT, which is an 8-meter ISO telescope, we saw that actually the blue main sequence stars are slightly more metal-rich than the red main sequence stars. So in order to be bluer and more metal-rich, then the hypothesis that was done is that these stars are actually helium-enhanced. So increasing the helium abundance, this stellar subpopulation shift towards the blue. So this is the hypothesis, the main hypothesis for the origin of this bluer main sequence of stars that you see here. Then this splitting of the main sequence was also served thanks to VLT, again with the 8-meter telescope, photometrically. And a few studies were published later, about 10 years ago or more, about the ratio of the number of blue main sequence stars over the number of red main sequence stars, because we wanted to understand if these 2 subpopulation in Omega Centauri at the same spatial distribution as a function of distance from the cluster center, you see here, up to, in this case, here 20 arc minutes from the center or 25 arc minutes. And you see here that the blue main sequence stars are more centrally concentrated. However, the ratio of blue to red main sequence stars distances and attains a flat value up to more or less 25 arc minutes. However, as I said, Omega Sun is a huge cluster, it's very extended. And from the literature, we know that the tidal or truncation radius is about 1 degree. So we know nothing about what happens from 25 arc minutes to 1 degree. And to investigate this area, we need field coverage. So Hubble cannot do it because Hubble has a field of view of 3 by 3 arc minutes. So you cannot get 1 degree field. And then you need also high photometric accuracy, equivalent or a little bit like less than Hubble. What we have done, we collected data for Omega Sun with DECA on the 4-meter Blanco telescope. So it's 4 meter instead of 8 of BLT, but still it's amazing camera, very good quality photometry. And the camera itself, it includes 62 different CCD, and we saw 5 different fields. So make your calculation, it was like a huge work to perform photometry on all these different CCD and put them at the same level and calibrate them, etc. We then combine the photometry from DECA with photometry that we had from the past, from HST in red, from the center of the cluster, and also from an ISO telescope, an ISO camera, wide field imager on the MPI telescope is a 2-meter telescope for this area here, the CN area. And the combined photometric catalog include about 3 million of stars, so a huge number of stars. As you see here in red, this is what we know from literature is the 1 degree truncation radius from Omega Sun. So this is a schematic view of how the mass and the light is distributed in a cluster. As you can see, most of the mass is actually towards the center of the cluster, what we call half mass radius. And for Omega Sun, it's like 5 arc minutes. But then we have still a lot, the other half of the mass of the cluster is distributed here up to the tidal radius where the surface density of the cluster declined to 0. So we want to understand what happens in this region. And now finally we have the data to actually do that. These are the color magnitude diagram that we obtained from DECA in different Sloan filter U, G, R, and I. And as you can see, it's not as nice as the color magnitude diagrams we were seeing before. And why is that? Because as I said, whenever we observe towards our object, we will be contaminated, especially if the field of view is huge, is very big, we will be contaminated by tons of other stars, in this case, disk stars, and they overlap with our cluster. So what do? We need to separate them. And we can use the motion of the stars, motion of stars in a cluster with very specific velocity, and the motion in the disk stars have a different one. And we could use Gaia, which provides proper motion of star. Yes, we can, but for the bright part, we cannot do that for the very faint main sequence we are interested in down here, because we want to see the blue and the remnant sequence. So we also devised a different method to separate the cluster from the field stars based on color, and magnitude diagram. Again, remember we have 4 different filters, and we have the U filter, which give us increased sensitivity to temperature of the star and also to metallicity. And metallicity of cluster stars is quite different from the metallicity of the field stars. So this allowed a very good separation between the cluster star that was validated by using the proper motion of Gaia for the bright stars. And we saw that it works quite well and gives us just a residual contamination from this star that is lower than 10%. These are the clean color magnitude diagram. As you remember, you saw something similar before for Omega Sun. You see the different red giant branch. This is the main one, mostly the most metal poor, and then you have metallicity increasing in this direction. You see not as well the different red giant branches here, but surprise, you see the splitting of the main sequence. So the blue main sequence and the red main sequence. This is again only a 4-meter telescope from the ground, and we were very happy to see that, and we decided then to study the distribution of the stars belonging to the blue main sequence in comparison to the distribution of the star belonging to the remnant sequence as a function of distance from the cluster center. So in order to select the blue main sequence stars and the red main sequence stars, we used here a color magnitude surface. So we divided the stars in a magnitude bin. This is I-band. You see it also here in two dimension only. And this is a surface density for the star. You see clearly there are two peaks, which are the blue main sequence, red main sequence peak, and a minimum between these two peaks. So we established that minimum, and then we started selecting stars around these ridge lines. So here you see it in green and cyan, with different color being, the color being G minus I. We started from the smallest was 0.02 magnitude, because this is equivalent to the average photometric error. And then we went increasing this color being up to 0.20 max, of course, just in this direction, because then we reach the minimum here and we can increase the color in that direction. And here you see the different selection for the different color beams. And you see a 3D view of the ratio of blue main sequence stars over the number of red main sequence stars as a function of distance from the cluster center. This is arc minute, so we get to about 2 degrees here. It's easier to visualize this in 2D. And these are the results from ACS VLT for the central part of the cluster, while in our case, we start from 10 arc minutes with DECA. You see the ratio starts to decrease up to 20 arc minutes. Then before, we didn't have any data for this region of the cluster, and now we have it. And we can see that this ratio is actually increasing, very steeply increasing up to what was before the truncation radius, so 1 degree. And then it flattens out and then increases again towards the outskirt of the classes. So this is a very interesting result, because it's true that the blue main sequence stars are more centrally concentrated in comparison to the red main sequence stars. But then if you look at the outskirt of the clusters, you see that they show also a more extended spatial distribution. So what we have done, we wanted to see if something similar was happening as well with the different population and different branches of the red giant branch, the different sequence on the red giant branch. This is a color magnitude diagram only for red giant branch stars. So we divided this in different groups according to the metallicity, because the redder the stars, the more metallic they are. So we call this group metal rich, the blue is metal poor, and then we have two metal intermediate groups. Of course, this is a relative study. We are not interested in the exact metal abundance of the stars, but just like in a relative metallicity. And as you can see here, we produce some isodensity of the different groups of stars. And especially if you look at this plot, you can see that the more metal-rich stars here, they show a more extended stellar distribution. And also the metal here, the purple one, the metal intermediate one, while the more metal poor stars, so these groups here, have less extended spatial distribution. The other important result is that the center of this group of stars is shifting different ways in comparison to the center, the geometrical center of the cluster, which is indicated with an X. The more metal-rich stars, these two groups, are shifted towards southeast, while the metal groups, also the metal intermediate green here, while the metal poor group, which is this blue dot, the center for this group, is shift 1 arc minutes north in comparison to the center of the cluster. So it looks like this population, yeah, they belong to the same cluster, but they have different properties. And this will, hold on, let me also briefly telling you about this. We also had this amazing 3 million stars catalog, and this allowed us for the first time to provide a density profile for Omega Centauri, which was based on faint sequence stars and bright red giant branch stars from the center of the cluster until beyond the tidal radius. And this is what you see, the density profile of the cluster for all the stars. We compare with theoretical models from King and Wilson here in all the plots. And this is the density profile of only the blue main sequence stellar population. This is for only the red main sequence population. And as you can see, it looks like the King and Wilson profile, they don't really work in reproducing the cluster density profile, especially a larger distance from the cluster center. And also, you see there are some stars that belong to the clusters, but they're here in the empty dots, and that we call potential escaper or a stellar halo around the cluster. And if you look at these three plots, there are more potential escaper stars belonging to the blue main sequence stars. But this, it was kind of expected since we saw that the blue main sequence stars have a more extended spatial distribution in comparison to the red main sequence stars. So summarizing, we found that the frequency of this blue main sequence star increases after 25 minutes. And there are some stellar halo or potential escaper present in Omega Centauri, maybe indicative of a recent discharging or emerging onto the stellar system. And at this point, what we want to do, since in dwarf galaxy, usually the matter-rich stellar population are more centrally concentrated in comparison to the more metal poor population, then we want to be sure that the blue main sequence stars in Omega Centauri are really more metal rich than the main sequence stars. So we need more data, essentially spectroscopy of these very faint stars, and that will be feasible hopefully with JWST and ISPEC in the future. And merging of a cluster is not happening right now in the Milky Way, but actually is observed for a young cluster in other galaxies around the Milky Way. For example, this image is from Hubble in the Magellanic Clouds. Then I talk a lot about globular cluster because I really like them. And now I will present you some results about the bulge. They're all published, so you can also read the papers to get more details on that. And the galaxy bulge are present in most galaxies again, and they contain the majority of the stellar mass of the universe. So the Milky Way bulge is the closest one that we can observe, and we can actually resolve the stars and study the stellar population here in very good detail, spectroscopically and photometrically. So characterizing the Milky Way bulge will also help us in understanding the bulges of farther away galaxies. And this is a WISE image in the infrared of the galaxies, and we confirm, this image actually confirmed that our bulge has also an X shape like it was found from photometric studies before. And also other galaxies, I don't know if you can see the X, but have this X shape and they're called pseudobulges. But then spectroscopy showed that most of the stars in this X shape are actually metal rich, while if you only select metal poor stars spectroscopically in the bulge, you actually don't observe the X shape. So if you only look at metal poor star, our bulge seems like a classical bulge. So these are only some of the open questions in the study of the galactic bulge. We want to understand if our bulge is 100% pseudo bulge, or if it includes also a classical component where most of the stars are metal poor. And also we like to understand how many different stellar populations are in the bulge. And most important, we have to solve a controversy about the presence of very young stars in the bulge. And I mean young stars 1, 2, 3, 4 gigayears. To do that, we can use wide field photometry, but we can, or surveys like BBB, for example, or we can use also HST. HST, of course, provides us a pencil beam, a very small field of view in a specific direction. In our case, we observed like a low reading window, so we could actually see the stars because we were not covered by a lot of dust that you see here in this image. You're coming towards the galactic center, so there's a lot of dust. And we obtain a very nice color magnitude diagram, but again, when you serve towards the galactic bulge, you're serving towards the disk as well. So this nice color magnitude diagram is contaminated by the presence of these stars. We select like a small sample of these stars here and a small sample of bulge stars here. And since we have observation performed at 2 different epochs, we could compare the position of the star and get their motion in between this time frame. So here you see the proper motion of the stars in milliarc second per year towards the galactic latitude and galactic longitude direction. And again, what do? These stars actually overlap with the bulge stars in this diagram. However, if you look at the longitude direction here, the 2 peaks of the bulge and the disk are actually separated. So what we did, we said, okay, let's select only 30% of bulge star, a very small fraction, but then we are essentially free of this contamination. This contamination is less than 1% by selecting only these stars. We highly decreased the number of bulge stars, but we really wanted to select only this stellar population component. We didn't want any mean sequence stars. Because what we wanted to do, it was to understand the mass function of the bulge and compare it to the mass function of the disk. And we wanted to understand if this mass function were similar. And here you see the color magnitude diagram. So with less stars, but still 70,000 stars, clean from the contamination. We don't have these stars. And we have a luminosity function, a magnitude function here. So to derive from this, the mass function, we need models. So we need luminosity mass ratio, and we can use isochrone for this for a fixed age for the bulge and metallicity. And we also need to correct for completeness of our observation, because the fainter we go when we observe stars, the less complete our observations are. So for that, we had to perform what we call artificial star test. So we corrected for completeness up to a completeness of 50% that you see here. Our observation, we use the models. So from our filter, here's the I band, we get a mass. So what we get is essentially a mass function. So number of stars as a function of mass. Also, we actually don't know the exact fraction of binaries in the bulge. And binaries really affect the mass function, because you are counting one star with a certain mass, but actually that's not one star, it's unresolved. It's actually 2 different stars with a different mass ratio. So you have to do some function on the fraction of binaries, and we did some tests starting from 0 up to 100%, and also on the distribution of the masses of this binary system. We use a flat distribution or a Duquesnoy-Mayor binary mass ratio distribution. In this particular plot, we assume the presence of 50% of binaries in the bulge, which is quite similar to the binaries that are present in the galactic disk, 50%. And I think this was for a flat binary distribution, if I'm not wrong. And as you can see, we plot some very known mass function, the Salpeter and Chabrier. And Salpeter mass function agrees quite well for the high mass end of the mass function here, up to, this is about 0.5 solar masses. However, when you go to lower masses here, Salpeter mass function is in disagreement with our observation that you see here in black with error bars. So we tried also to compare with Chabrier mass function, which is actually in quite a good agreement. And then we decided to fit our mass function with 2 different slopes that you see here dotted, and the second slope here dashed, this dashed line. And the 2 slopes that we found, the first one for the high mass range is -235. As I said, very good agreement with Salpeter. And then for masses lower than 0.5 solar mass, we found -126, this is the error. And actually, these 2 slopes are in very good agreement with the mass function that was found by Krupa for the galactic disk. Then what we did was to combine our proper motion for the galactic bulge and photometry with photometry that was collected before with HST again. This is Wi-Fi camera 3. And the filters that were used in Wi-Fi camera 3 were, again, there was the U band and the G band, and combining this, and also the infrared observation. Combining these filters, we created two indexes, one for the metallicity, you see here, and one for the temperature of the star. And this is the density plot in this color plane, so all photometry. And you can see that there are two different peaks here in metallicity. And so we were able to divide the stars in a metal poor component and a metal rich component, which you can see here with the ridge line on the color magnitude diagram for a well-selected magnitude interval on the main sequence. Then we had proper motion from the previous studies here that I show you. We had this proper motion. We combined metallicity information with proper motion, and we plotted as a function of distance from Earth down to the galactic bulge. And red is the metal-rich group of stars. And still, it's in bracket. We are interested in the relative metallicity distance between the stars, not to get a very accurate metallicity estimate for these stars, for these main sequence stars. This is a sample of 10,000 main sequence stars. And as you can see, the metal-rich stars actually show higher rotation compared to the metal poor stars. And this was confirming results that were based on radial velocity, so not proper motion, but radial velocity of the less common red giant branch stars in the bulge. So we were very happy about that. And then we were saying, okay, there are some studies based on spectroscopy of dwarf stars that are microlens, so they get brighter and you can get a higher signal to a spectrum. And this spectroscopy study, published a few years ago, they claim that 1/4, which is a lot, of bulge stars are actually younger than 5 gigayear. And then we said, we have a color magnitude diagram from a small direction, pencil beam towards the bulge. And the main sequence turnoff, as I said before, is an indicator of the age of the stellar population. So if there is a spread in age and all these stars so young, we should see a huge spread here in luminosity of the main sequence turnoff. So these models that are plotted here, isochrones for 11 gigayears, you see, they don't leave much room to a younger population. There could be some stars here that are younger since they're more luminous of this turnoff, but they're not more than 5% of the stellar population, at least in this field. So this is a huge controversy, 26% versus less than 5%. And actually, this is not resolved yet. So it will be amazing to have like an HST that can observe essentially the entire bulge. And hopefully this will happen with WFIRST, which is a telescope that will be launched in hopefully 4 or 5 years, and will allow us, like, it will have similar resolution of HST, but a huge field of view. And maybe we'll be able to see if, observing in other direction, there are more young stars in the bulge. But for sure here, we don't see this. Also, we have some wide field data for the bulge, not only the VVV serving the infrared, but we actually observed the bulge with DECAM, again, the amazing 62 CCD camera. And we were able to correct for extinction this color magnitude diagram by using essentially R-Lyre observation with DECAM. And so this, as you see here, is corrected for extinction. And why for extinction? Because again, observing through, towards the bulge, you have a lot of gas and dust in front of you. And this makes your color magnitude diagram to spread like this in color. So your sequences are confused. But we managed to correct it so we can see very well-defined sequences. But again, this is a 4-meter, DECAM is on a 4-meter telescope, so you cannot really study in detail the main sequence. For this, you need HST, but HST is 3 by 3 arc minutes, very small field of view, while DECAM is 2 by 2 degrees. So it's very complicated. But these data are like complementary. And what we saw here, except the earlier stars, as I said, but also this weird plume of stars appeared that we call blue loop stars. They are about, probably the stars that are here about 5,000, and the stars in the Collaborators diagram that you're seeing are almost 1 million stars. And 10 of these stars have spectroscopy from a survey, spectroscopic survey from the ground apogee. And we saw that they're all very matter rich, and their mass is about 2 solar masses. But again, it's only 10 out of 10,000 and 1 million. So for sure, in order to understand if these blue loop stars represent the possible young component of the bulge, we need more spectroscopy. But even if they are, they're still less than 5% of the bulge stars. So there's still this controversy that we don't see 26% of the bulge stars that are young. And this is a quite big field of view, 2 by 2 degrees. So for the bulge, assuming we found that the mass function down to 0.15 solar masses is in very good agreement with this mass function. And the matter-rich stars show a higher rotation compared to matter-poor stars. And there are 2 very different stellar population components of the bulge. Future projects. So of course, we still have a lot of work to do for globular cluster and also for the galactic bulge. For globular cluster, we intend to perform similar study of the spatial distribution of different stellar population from the center to the escort. And to constrain, we want to constrain the density profile of this cluster, their truncation or tidal radii, and if they have extra tidal or halo stars or potential escaper. To do that, we want to combine DECAM and MegaCam data with HST data that are available already for most galactic globular clusters. But in the future, we can perform similar study with LSST and the amazing W4 that will be launched again in 4 years. And for the center of this cluster, we can use JWST. Hopefully will be launched in 6 months. For the galactic bulge, we want to constrain the 3D metallicity and extinction map, for example, by using R-Laris stars, and better constrain the presence of a young population. We need spectroscopy. So again, we need JWST data, for example, for spectroscopy, and the LSST or W4s to study the bright component, and to study LSST in particular to study the R-Laris stars in the bulge. This is just a schematic of what will happen if we start with JWST, spectrograph the center of Omega Centauri. We will have these 4 feeds to get the metallicity of the blue and the red mid sequence. We have data for many other globular clusters which are already available from DECAM and MegaCam, and again, HST is already available. You see here a list of clusters, and we will be able to fund students interested in working in this project for 6 months or 1 year of stay at the Space Telescope with the DDRF, it's the Director Distraction Research Funding, but also Space Telescope, a very nice Space Astronomy Summer Program, SASP. Here you see the link, and you can actually Google SASP Space Telescope, and you will get to this program. In 2020, it was all online, virtual, but it was very successful. You can find information of and results presented by the different students. And in 2021, unfortunately, this summer will be virtual again, but I think it's worth the experience. You will work for a research project in collaboration with us at Space Telescope. But if you want, you can also work for a more technical project with one of the instruments, either on Hubble or actually also on JWST, which, JWST is going to be launched in a few months. So if you work this summer, it will be just 3 months before the launch. So there will be interesting things to do. And with this, I'm done. Thank you for your attention.